Okay, guys, thermodynamics, we'll eventually come back to that. There's calculations, hopefully you have done those. We'll do those quickly at some point. If you have questions, please be asking. We need to move ahead with alkene reactions. This afternoon, we'll meet downstairs for lab. There will be a lab lecture component. That is material that's lecture material. Here's our outline. We're going to be making our way through all these reactions. All of these. Sort of in the order. Boom, and then around in a certain order there. Addition of HX to alkenes. It's our handout. We did this mechanism up here. Reaction of this alkene with HBr. Addition of HBr to the alkene. Here's your mechanism. How many intermediates were there? One intermediate. It's called a carbocation intermediate. Rate determining step. Addition of the bromide to the carbocation. Fast step. That's the last, and that's the fast step here. Any questions about this? Then we'll get going. Question, this carbocation, the plus is on this carbon here. You need to draw charges very near to the atom. Is this carbon here primary, secondary, tertiary? Tertiary. Yes, it's a tertiary carbocation. Okay? We're always going to classify our carbocations because that's very important. We'll say that below. Okay. With your reaction coordinate diagram, we were ending this reaction thermodynamically favored. Yes, you can pull out your calculator and do a calculation, but you can also tell that because we're going from a pi bond. Pi bond was broken, two sigma bonds, two stronger bonds were formed. That should be exothermic. You just look at it like that. But this reaction is not favored by entropy because two molecules are combining to go to one. Not favored by entropy. Make sense? So is it favored overall? That's a tougher question because that's the delta G. Okay? It's a little bit tougher. Let me ask you this. See how we're doing this morning on this Friday morning. If this reaction was a little bit slow, we don't know what the rate is. Would you want to heat it to make it faster? Would you want to heat this reaction up to make it faster?
No.
Under low temperature. It's the acid, it's gonna.
Yeah.
Why not heat it?
You told us not to heat them in the lab for the first lab with the acids, so I imagine you wouldn't do it here.
There might
No,
be.
that's because I wanted you to get the result I wanted you to get. If you heated it, it would dissolve, but it wouldn't be because of the acid.
Is it favorable?
That's not,
Favorable under lower temperature?
it's more favorable under lower temperature. Why?
Because of entropy?
Entropy, yes. Entropy is not good. Which term, what does temperature do to the entropy term in your delta G?
Increases it.
It magnifies it. So if you got a bad term, do you want to magnify it by heating? It's going to make it even badder, worse. Right? No, you would not want to heat this if you understand T delta S. Right? Gen Chem, right? You talked about heating reactions, yeah?
Do you have an extra copy of that packet? If not, I can come to see you.
Thank you.
Thank you very much.
Okay, let's move ahead. Why does this reaction not give this product? Same reaction. Is that product different? Yes. What type of halide did we make up here? This is an alkyl halide, right? Alkyl bromide. Can we classify? The bromine is on a tertiary carbon, so we can call this a tertiary alkyl halide. Yeah? What type of, down here I'm showing what type of alkyl halide. Yeah. Why does this reaction not give the primary halide? What's the difference? Up here, we have HBr across the pi bond, these two carbons. But up here, the bromine was here and the H was here. By the way, you got to make sure you know where your new H's are. There's a new H on the end, right? You guys always forget UHs and where they're at, and that causes you problems down there, okay? Why not have the outcome where the H is here and the bromine is there, which is the product shown below? Why not that product? Well, first off, let's do a mechanism for that and compare our mechanisms. This would involve, well, what's going on here? We can consider this ionic or covalent. And I'll allow you to just show it ionic instead of having to do a mechanism to get there. Okay? Pi bond attacks the H plus. These two electrons are held loose. Okay? Let's make pi bond. Correct. Pi bond. All right? Strong sigma bond, but then you got this weaker pi bond. It's like, okay? H plus over here.
H plus.
H plus.
H plus. These electrons are like, ooh, H plus. Sorry, carbon, but I'm going to go make bond over here and leave you without a bond. These electrons gravitate towards that H plus. It's physics. So, somebody pull my arm. Not my finger, but my arm. Pull it and yank it and make it go bond over there. That's what we're doing with the arrow. Pull this away from this carbon and make it go there. Okay? Here we go. I'll do this many times. Here's the pi bond. Yank my arm and go make bond to H. But my arm is still connected to this carbon. My hand just broke away from over there. Okay? That's the movement. What does this arrow movement give? Or WDAM. What does arrow mean? It means that it went and made a bond, and we can draw a result of that. Boom, boom, boom. And now we have bond to H. Pi bond was here, but it hinged up, and now we have bond to H. But this is now missing a bond, and that is indeed now a plus. Well, hold on. I'm doing it the right way. That's not going to give this product because this product has a new H here. Got the BR out there. This is actually the right way. I'll leave that there. We need to attack, sort of have the H plus over here. We need to hinge the other way. That is, hinge this way and come like this, and that would give, coming over here, boop, 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 H. Used to be pi bond, but it went and bonded to H. Now what's over here? It's missing a bond. Plus. All right? You got to know that this is, you're going to get confused with this. It's like, it's only got one bond. No, there's two. There's two H's here. There's two H's there. Total of 3 bonds. Positive charge. Now, if we get to this part, now we can envision getting this by what? Now the bromide, boom, nucleophilic addition of the bromide. These electrons making bond here, minus tracking to the plus, making bond, that would give this product. But why does this mechanism not occur? Why does the one above occur instead? It's all because of the first step. The first step here, we formed what type of cation? Primary, secondary, tertiary? Primary. Bad. What type did we form at the top, which I also did here? Tertiary. Good. Why is tertiary much better? This is a carbon with a plus, called a carbocation. How do you stabilize a plus? You push electrons towards it. And there's different ways. You can do that by resonance or by induction. All you got here possible is induction. sp3 carbon inductively donates, and you have like 3 chains there because it's tertiary. This guy only has 1. Even though there's more carbons, it's only 1 chain coming into this. Not as much induction. Better cation. This is the way the reaction is going to go. If we look back at reaction coordinate diagram in thermodynamics handout, very top up here, This is the exact reaction we're doing. Here's the two different cations shown. They've drawn them out with all the carbons and H's. This one's primary, and this one's tertiary. This one's more stable. We already sort of answered that. So if you plotted these two potential pathways, mechanisms, the first step of each, okay, two different intermediates possible. But the tertiary is lower in energy. Because of that, the transition state leading to it should be lower in energy. So, here you go. The reaction has a choice. Which way is it going to go? It's going to go the least lower energy pathway, and you get the tertiary cation. You get this cation. Since you get that cation, the bromide attacks the cation, and you end up with the product at the top. It does not follow the lower pathway. That mechanism doesn't occur because it would require energy to run uphill. And if you ever see water running uphill, when it can go downhill, let me know. Now in a hurricane, maybe you'll see water running uphill.
It's because it's got wind behind it.
And we'll mention that sometimes because... Does that mean that this product, the other product, will never occur? Well, I'm saying absolutely no, but maybe 1% of the time there's enough, it's like water. Does water never go kind of up? Well, if it's coming real fast, it might go up a little bit, but it ain't going to go up preferentially. And usually we're always looking to give the preferred product. That doesn't mean it's the only product. The preferred product in our first mechanism here is the one at the top, the tertiary halide, not the primary halide. So, the above reaction is called regioselective. Here, the bromine bonded sort of at this region of the compound. Another way to say regio is, might be a little bit more intuitive, is site selective. But you'll never kind of hear that. You'll always be called regioselective. The bromine added at this site had two choices, this site or that site. Was it selective over one of those, or was it just random? No, it was selective, and hopefully I explained why. This reaction is site selective, but we need to call it regioselective. Yes. Why? Why? Because of carbocation stability of our intermediate. That's why. Here's your ranking. By the way, that's not even primary. That's considered just parent or base. That's your worst cation. Here are cations. These are okay. These are good. Tertiary is better. We'll typically never form a primary cation unless we absolutely have to. Primary is considered bad, and that's thus kind of quite bad. So we'll always be leery about these. These will be preferred. Tertiary is best. Other things do affect carbocation stability, though, such as resonance. And we'll see some examples of that along the way. The effect on the reaction coordinate diagram, that's what we looked at when we referred to the other page. Okay. Our basic mechanism. The mechanism is like in math when you have an equation. I had math for a long time. Do you still use equations? If you have an equation, then you're like, throw me any number. I'll give you the answer because I know how to do it. Throw me any number. You don't memorize every single one, do you? What's 56 times 12? Oh, you're thinking, how do I do this? But you know you can do it, right? Mm-hmm. Right. You didn't memorize 56 by 12. So do you know how to do reactions? Well, we did the mechanism. That's how you do the reaction. Okay, so how do you do this one? Well, the pi bond is, let's repeat, okay? You have like the old repeat mode. Let's repeat. Pi bond is a source of electrons. Pi bond can attack H+. Do we have a pi bond? Do we have H+? We can show it covalent or ionic. This is all repeat mode now, right? Reaction of an alkene with HX gives what? An alkyl halide. It's all repeat from now. But you have to assess what you have here. Okay? So, form the carbocation, because forming the carbocation is the first step of hydrohalogenation mechanism. Can you show the carbocation? We have a choice. Are we going to make cation at top or bottom? That's ultimately our choice. Well, think about it. If you envision a carbocation, would you rather have it at top or bottom? On top, because you can see it would be tertiary? Yes. So we can sort of, this is going to hinge down. You can pull whichever. I mean, you can just pull this down. If you think that's the sigma and that's the pi. But hinge it down, and that's going to give, by the way, I'm not just going to throw a product up there. I would never do that to you, because I don't want you to just throw a product up there. I want you to understand the process of how to get to it, because that's really more important. That will allow you to do anything. So we get, a lot of times I'll draw in the new H. This is hinging down, and now it's bonded to the H down here. And I'll indicate, hey, we just made that bond. So when you're looking at this, you'll see what that means. Now my rings are not often all together. I mean, are these all bonded? Yeah, okay. I won't take time to... What's up here though now, when that hinged down? Missing a bond. There's your carbocation. All right, and it's tertiary. If we had hinged up, that would have been a secondary cation. Not as good. Okay? That's your first step. That's your rate determining step. What's the second step? The Cl minus, these electrons, okay? Every time you show a mechanism error, you start by saying these electrons. That is, these two electrons hinge down and make bond to H. Now, these two electrons go attack and make bond to plus, because negatives like pluses. It's as simple as that. We're not getting into the book that thick about how a bond is made. That's going to make a covalent bond. And what does that give? Well, that's going to be your final product. What will it look like? Is that it?
You're missing a bond,
A what?
a bond on the CL because it was already there.
Methyl group?
Yeah.
Did I forget something?
The original methyl.
Oh, the methyl? I lost it? You mean like that?
Yeah.
Good. Don't make that mistake. Common mistake is for you guys just to not show everything that should be there. There's nothing there. Again, this is, I'll never get them together. Okay. Anything else? Any questions? Tertiary alkyl chloride? That's a product? Whatever formula this is, this formula now has HCl added to it. We did an addition of HCl to an alkene. I'm wondering, I thought someone would say, where's the H? Anybody know where the H is at?
It's implied.
It's implied, it's still there.
It's there. Actually, how many are there?
2.
2. How many were here?
One.
Only one. There's a new one there. Why did I draw it in here but not there?
To
Show that it was understood.
Because over here is where I added the H, and I'm choosing to show, hey, I added the H, I showed you what bond, but over here, I no longer chose to show it. You have to know this. This is just my style, because that's ultimately shown in a standard line bond structure where we don't show H's. So this is just for illustration, though, but to help us be clear here, clarity. I hope you understand this. There's your product that you would predict. Okay, predict the next product. Boom. Next two, but we'll do the next one first. Somebody have it? Have a name for it? 2-iodopentane? Yeah, 2-iodopentane. Product is going to be boom, 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 boom. Iodine here. Okay. Yeah? Why is the iodine there? Because that's where the cation would be. When this thing goes and attacks the H+, is it going to hinge this way and put cation here? Or hinge this way and put cation here? H and cation, no. You can put H here and cation here. So we got H+, I minus. This comes this way, hinges out. Make your arrow mean something. You're pulling it away from this carbon. Sometimes you guys just sort of do this, and it's just kind of, well, what are you really showing here? Yank it away from that carbon, boom, and then attack something. H+. The cation then form, boom, 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 boom. Cation here, yeah? There's a new H out here, right? It has to be, because that structure, there's 3 H's. Here there's only 2. Again, I like to draw in the new H. Then the I attacks here. You can finish it up. The first 2 reactions, are they regioselective? How about this? What would be the regioisomer that's potentially formed up here? The other regioisomer is what it's called. What would it look like at the top?
The second carbon.
We'd have the chlorine here and the H up here. That would be the regioisomer in the context of this reaction. Do you get both? Maybe equally, or do you only get one as the major product?
One is the major product.
Right. It's regioselective. How about the second reaction? Do you get the iodine on the N carbon as well? Certainly not as the major product. Both of these are regioselective. How about the third one? What's your product down there? Can you name it? Or is it more like vague of what you're going to get here?
More
Either-
vague.
Are you going to make cation on left or right?
Does it matter because they're the same, they're both
They
secondary?
both would be secondary. So do you predict this reaction to be selective?
No.
Why would it choose one secondary over the other? I'd give you no reason why it would. What are the 2 possible? There's 2 possible products here. There's no selectivity here. Does everybody see that? Understanding. 2 possible products here is boom, 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 boom. The iodine can end up here, Or it could end up you can either get 2 iodopentane or 3 iodopentane. Not regioselective. Both cases would be secondary cations. There's no reason to choose one over the other. This being 2 iodopentane. Let me ask you this. A lot of times we maybe are given a product and then ask, what would be the best way to make this product? Of these 2 reactions here, it's 2 different reactions because we've got 2 different star materials. Which reaction would you choose, top or bottom, if you wanted to make 2 iodopentane in the highest yield?
The top one.
Top one, right? Because the top reaction is going to selectively give 2 iodopentane. The bottom reaction would not. It would also give 3 iodopentane, theoretically.
Do you find experimentally that it's about half and half? When you do
Down
that?
here,
Yeah.
it can vary a little bit, but roughly I would say, yeah, it'd be about half and half. A lot of times there's advanced things going on to make it maybe 60-40. And then you're like, well, is 60-40 considered selective? We won't get into that. Okay, so that would be like synthesis. And let's look at that a little bit more. Can you provide a high-yielding regioselective synthesis of this? How would you make this compound? I'll give you a compound, common question is, tell me how you would make it. One thing you need is a starting material. What do you want to start with? Because this is up to you to come up with. And then what reagents would you use to react that with? This is synthesis. Well, you're being asked to make an alkyl halide. Have you ever seen a reaction that gives an alkyl halide as a product? It's the only one we've done so far. Reaction of an alkene with HBr. Now, when you get over to organic 2, or even later in this semester, you may know 2 or 3 ways to make such a product. Maybe multiple. Right now, you only know one, and that's reacting an alkene with HBr. So what alkene would you use? Can you show the alkene? Well, it's very similar to the one above. Would you use that alkene, or would you use... Which alkene would be best? This would be best. It's the same as what we looked at above. Because here, you would selectively form cation there, secondary. But here, it would be either. So I would react this with what?
HBr.
HBr. There's your synthesis. Let me blow your mind. Could we use something other than HBr? Well, obviously we can't use HCl, because it ain't going to turn it from. But let me just kind of advance this a little bit. Could we use maybe H2SO4 and KBr?
Yes.
Would that work? How in the world might that work? What do you need to do this reaction? What does this react with first? H plus. Okay. Is there any H plus in this mix? So if your gas, it is a great source of H plus. Reacts with H plus, form a carbocation. Then what attacks the carbocation?
HBr.
Br minus. Is there any Br minus in that reaction? Yeah. So everything you need is here as well. Right? Okay. Now this is a little bit, you're always going to see HBr. But when you see this, don't like be surprised or praised about it. Everything is there. How about the one on the right? Obviously, we're going to react some alkene with HCl. Do you have the alkene? What alkene would you use? How about that one? How about that one there?
Yeah.
So HCl. Where are you going to make cation? Left or right?
Left.
Left would be a tertiary cation. You got to be able to envision these. Cation there and then Cl minus added there. That looks like a regioselective synthesis. But is there another alkene you could use?
I guess if I want to be on this part.
Like that? Well, let's first look at this. My question was, is there another alkene you could use? Problem with that is that's the same alkene. You see that? That's just, because if you name them, it's the same exact name. So that's really not another alkene. That's just, all right. But some double bond. Well, we could have a double bond like that. Would that be regioselective, or we're going to make cation on top or bottom? Top. Both of these reaction mechanisms involve the same intermediate. Both involve forming. They both give the same intermediate. Now, eventually we'll maybe ask, which route would be faster as in terms of the reaction being faster? Might think about that. We'll come back and hit on that at some point, but that's a nice setup to ask that question. Which reaction would be faster? You know, we could call this A and this B. They both involve. How do you get this? You consider reaction coordinate diagrams. Maybe plot them out for each. Where would you see differences? And where you see differences, that's where you want to get your answer. That's how you would get it there. Okay, down below, which product is formed? Down here. Huh. Anybody got this one? Rather make cation on top or bottom? What do you think about this? Why top?
Because the rim is on the right.
You need to think about this.
I'm gonna say bottom because of that oxygen.
Still need to think about this.
Because of resonance.
What was that?
Resonance.
Resonance. Okay. In addition to induction, primary, secondary, tertiary, resonance is also an important consideration of how you stabilize cations. And you got potential for resonance here. Think about it. We'll come back and touch on this. Okay, next reaction, and if I showed you the yellow, we'd just be moving along to the next reaction. The next reaction on the yellow is hydration of alkenes. Hydration, water, adding water to alkenes. This is going to give alcohols. Not alkyl halides, alcohols. Okay. Alkenes, however, don't react with pure water. No reaction with pure water. Water is not reactive enough. It's not electrophilic enough. That is your water over here. Yeah. Yeah. Okay. Pi bond, your water. I'm just not interested in water. You know, you're not reactive enough. I'm not going to go. Okay. No reaction. So how do we add water to an alkene if it don't react with water? By the way, the skin of an apple is largely made up of alkenes.
Got waxy.
They actually protect the apple from the water. If the alkenes reacted with water, your apple would just degrade when it rained on the tree. Okay? But acid rain is a different case. Because acid rain brings in acid, and acid can act as a catalyst. This reaction will occur if you bring in H plus catalyst. And we can get a product. And if you look at the products, we've added water. And this is just catalyst. Addition of water. Okay? Now, I showed this as water and H plus. But usually that will be shown as this. H3O plus is water and H plus. It's aqueous acid. Now, what type of H plus catalyst is usually used here? Sulfuric acid, phosphoric acid, or even HF. That's a good acid for these reactions. You would not want to use HBr or HCl. Because if you use that, you would end up with the previous reaction, the alkyl halide product. So your choice of acid is important. The reason you can use HF is because F minus will not attack the cation typically. It's a poor nucleophile, so it won't do the previous chemistry. That's why when we defined HX previously, we did not say it was F. So those are sources of your H plus. Here's your mechanism. The first step is the same. We have H plus. In this case, it comes from the catalyst. Pi bond attacks H plus. Where are we going to leave cation? Left or right?
Left.
On the left. It's the same thing as before. Tertiary cation, right? That's what we would predict. What can attack the cation? In this case, the answer is water. Not Br minus, not Cl minus. Water. And these electrons make bond to cation. So we just made this bond. Now that's not the end product, because this oxygen has two H's. You see them there? And when I did this, do the H's disappear? When these electrons make bond here, does that cause the H's to disappear? No. Now, I know on some of your quizzes and tests, this will happen. They'll just disappear. Don't let them disappear. Everything you show here had to come from the arrow. If you want the H's to disappear, you've got to show an arrow or something. They're still there. The oxygen is now the oxygen is a positive charge because if you can do a charge, it's an atypical oxygen. But this can go neutral by losing an H, by acting as an acid. Now here, the conjugate base of the original acid will retake it. Now, I sort of let you get away with this here, and we'll discuss. First off, I'm not showing a full Lewis structure. If I did, it would be here, this is your bisulfate. And these electrons take H. These electrons move on to oxygen. Standard acid-base reaction. This produces H2SO4. This produces your final product. What does this arrow mean to you? By the way, this arrow, we're pulling the electrons away from the H. Some of you on the test showed an arrow that looked like this. And while that's close, like in horseshoes, close doesn't always count, and I gave you only half credit. The electrons are coming away from the H, so a little more precision with the arrow movement to give a second lone pair, and that's the product, and we reform sulfuric acid, which is the catalyst. That is, the initial H was the catalyst. We reform it by losing an H from water, essentially. Now, I always like to use the exact conjugate base of the acid. That way we can reform the acid. But it's actually more correct to use water to take the H. Because this is aqueous. If we use water to take the H, we form this plus what? H3O plus. That's actually more correct, because how does sulfuric acid exist in water? It exists like that, right? So it's certainly fine to just use water. But again, I like to use the exact conjugate base, so we form the exact acid. That's just my style and preference. I think it's a little bit less confusing, but it's actually more correct to use water there.
So we can use either or.
You can do either one. I'm not going to count you off for doing it more correctly than me. Everybody understand? That is, how does sulfuric acid exist in water? Ionized. What does ionized mean? It's going to be, for example, HSO4 minus. And what else? The H will sit with, the H sits with water. This is how it actually exists in water. So to get to that point, you would use water here to take the H and form this, and just leave the anion as an anion. Okay, that's the way I typically do it. Your textbook may use water. So this is your hydration mechanism. How many total steps in the mechanism? 3. Previous mechanism only had 2. 3 here because when the nucleophile added to the cation, we were not done. We still then had to have a next step where we remove proton from oxygen to go neutral. So this was actually 3. How many intermediates in this reaction? 2. The carbocation. But we also had this intermediate, this one, the protonated oxygen intermediate. Is it not? Yes, it's an intermediate. So if we plotted this reaction coordinate diagram, we would have 2 intermediates. Now, this reaction is actually reversible. And that is, you can take an alcohol and remove water to make an alkene. You remove water. And that's the reverse. And the removal is also catalyzed by acid. This mechanism is actually, every step is reversible. Now, this reaction is going this way is covered either near the end of this course or in Organic 2. And when you do it, it'll just be the reverse. Right there. That is, the first step will be to protonate the oxygen. Then the next step will be water leaving. And that would be the idea of leaving groups. Can something turn around and leave? Yes. So I'm just pointing this out because that's just in the future. So this reaction is one that's commonly known as being reversible. Right now we're going the alkene to the alcohol direction. Predict the products down here. These 2 here, first one and then second one. How's that look? Might need a little bit more time. Here's your product. What are you thinking? This attacks H plus. Do we have H plus? What is this? H plus in water. Alkene attacks H plus. Where do we make cation? Left or right?
Left.
On the left. What attacks cation in this reaction?
OH.
Water. So it attacks the second carbon. Well, what happened to the other H? Because water has two H's.
So it was a
We
fire.
lost it in that last step. It's all there. Yeah? Where's the new H at? It's actually on the end. There's 3 there now. Only 2 on the end to begin with. We got a new H on the end, and we got a new H here and an O. We've added H2O to the compound. Overall, essentially. We have hydrated the alkene. Not with pure water, but with acidic water. Acid, catalyst.
The H that was lost, would you just, you don't write it or anything? Think why?
Typically, you're looking for the major organic product. But if you want to fully balance this, we have, you could call this H plus in water. These two react to give that plus H plus. The H plus is the catalyst. Definition of catalyst, it's reformed. It's there at the end. What's missing here? A minus. You cannot go to the stockroom and say, give me some H plus. They're going to say, well, what do you want to go with it? So this is generic. Maybe the minus is HSO4 minus. And if you show this totally together, this would be H2SO4, right? H plus doesn't exist by itself. You could show this as HSO4 minus, or you can just show it as H2SO4. Basically, you got some acid, sulfuric acid, at the end it's going to still be there. But it's reformed by... So you got to get those nuances, those intricate details just set in your mind. Figure it out. Problem is, there's multiple ways to show it. If I only did one way, and then you go into biochem and that professor chooses to do it the other way, or that textbook, then you're going to be like, whoa. So we look at different ways. Different ways to do the same thing. Tomato, tomato, potato, potato. Amide, amide, amide. How about the bottom one? What's going on down there? By the way, I raised the product up here. Let me read you out real quick. Stereochemistry. Does this product have any stereochemistry? Basically, at this point, this is just to help get us started. The answer is yes. What type of stereochemistry is possible here? Enantiomers. Enantiomers is abbreviated, particularly in the Klein textbook, is just EN. EN. Okay? Enantiomers are possible here. Those who were in lab yesterday, do you see possibility of enantiomers here? Due to what? Structural feature. You see a chiral carbon, and when you see a chiral carbon, you know there's 2 possible configurations with R and S. Yeah, those are the 2 enantiomers. More this afternoon in lab. This is just sort of setting the seed, so when we get there, you'll have it in your notes. But the stereochemistry here is important. Down here, what's going on? Alkene. I don't see any water. I see some acid, HF.
So,
What is the ethanol? Well, let's look back up here at the water. When this oxygen reacted here, does it have to have 2 H's on it?
No. H plus and OH minus.
Hydroxide can form.
Could have been one H and maybe an R group.
Yeah.
Could this oxygen have a tech? Yeah, it's just presence of an R group is not going to change anything. And that's what's going on in the reaction below. Now, when you get over here and one's R and one's H, you're going to lose the H. You're not going to lose the R, so it'll still be there. Now, if they were both R, then you got some problems. So look at that and see if you can predict product. Please be looking ahead. Next topic. Okay, remember the yellow also contains our outline. All right, make sure that we're hitting all the topics. Outline, right? Where are we at? Oh, really? We ended with 3. Number 4. Please be reading in your textbook. Carbocati and rearrangements.